The Wilkinson power divider, invented by Ernest J. Wilkinson in 1960, is a masterpiece of microwave engineering. To appreciate it, you first have to understand the fundamental flaw of a simple T-junction, splitting one wire into two. According to microwave network theory, it is physically impossible for a lossless, reciprocal three-port network to be perfectly matched at all three ports simultaneously. If you build a simple lossless T-junction and match the input, the output ports will inevitably have severe reflections and zero isolation. If a signal bounces off an antenna at port 2, it will travel right into port 3 and destroy whatever receiver is connected there. The Wilkinson divider solves this elegantly by introducing a single lossy component, a resistor, in a way that it dissipates zero power during normal operation, but absorbs 100% of the reflected power when things go wrong. The anatomy of a Wilkinson. A standard equal-split Wilkinson power divider operating in a system with characteristic impedance Z0, usually 50 ohm, consists of port 1, the input, two quarter-wave lines. The input splits into two parallel transmission lines. The characteristic impedance of these lines is exactly square root of Z0, about 70.7 ohm. Ports 2 and 3, the outputs. The isolation resistor. A resistor with a value of 2 times Z0, 100 ohm, is connected directly between port 2 and port 3. Conceptual operation. When you inject power into port 1, it splits evenly. Because the structure is perfectly symmetric, the voltage at port 2 is exactly the same as the voltage at port 3. Since there is no voltage difference across the 100 ohm resistor, no current flows through it. It is completely invisible to the forward traveling wave. However, if a wave enters port 2, it splits. Half goes back to port 1 and half travels across the resistor. The genius of the quarter wave lines is that they create a perfect 180-degree phase cancellation at port 3, completely isolating it from port 2. To prove this mathematically, we must use even-odd mode analysis. 2. Even-odd mode analysis. Because the Wilkinson is completely symmetric along its horizontal axis, we can analyze complex excitations by breaking them into two simpler symmetric states, the even mode and the odd mode. By calculating the circuit's response to each mode separately and superimposing them, we can find the complete S parameters. Imagine we are testing the isolation and matching of port 2. We inject a voltage of V into port 2 and 0 volt into port 3. We can mathematically define this state as the sum of an even excitation and an odd excitation. Even mode, V2 equals V over 2 and V3 equals V over 2. Odd mode, V2 equals V over 2 and V3 equals negative V over 2. Notice that adding these together yields V2 equals V and V3 equals 0, exactly our test condition. A. The even mode, in-phase excitation. In the even mode, identical waves enter port 2 and port 3. The resistor. Because V2 equals V3, there is no voltage drop across the 2 times Z0 resistor. No current flows through it. We can mathematically slice the resistor in half and treat it as two open circuits. The split, port 1. The two waves travel up the quarter wave arms and meet at port 1. Because we are analyzing one half of the symmetric circuit, we split the port 1 termination, Z0, into two parallel resistors of 2 times Z0. The calculation. Look into port 2. You see a quarter wave transmission line with an impedance of Z1 equals square root of 2 times Z0, terminated by a load of ZL equals 2 times Z0. We use the standard quarter wave transformer formula we derived previously. Zn even equals Z1 squared over ZL equals Z0. Conclusion for even mode, the input impedance looking into port 2 is exactly Z0. The port is perfectly matched. B. The odd mode, out of phase excitation. In the odd mode, the wave entering port 2 is exactly 180 degrees out of phase with the wave entering port 3. The axis of symmetry. Because the top half of the circuit is positive and the bottom half is negative, the exact middle of the circuit must be 0 volt. This creates a virtual short circuit along the axis of symmetry. The resistor. The virtual short slices the 2 times Z0 resistor in half, grounding the middle. Therefore, port 2 sees a resistor of exactly Z0 connected to ground. The split, port 1. The virtual short also grounds port 1. The calculation. Look into port 2. you see two things in parallel. The split resistor, Z0, to ground. A quarter wave transmission line that is shorted to ground at the far end, port 1. What is the input impedance of a shorted quarter wave line? Z shorted equals JZ1 tan 90 degrees to infinity. A shorted quarter wave line acts as a perfect open circuit. It completely disappears from the equation. All that is left is the split resistor. Zn odd equals Z0 parallel infinity equals Z0. Conclusion for odd mode. The input impedance looking into port 2 is exactly Z0. The port is perfectly matched and all power is absorbed by the resistor.
C. The superposition result. Since port 2 is perfectly matched in both the even mode and the odd mode, it must be perfectly matched when they are combined. S22 equals 0, and by symmetry, S33 equals 0. What about isolation, S32? When we drove port 2, we found that in the odd mode, all power was entirely dissipated as heat inside the resistor. Because the power never makes it to port 3, the shorted quarter wave line blocked it. Port 2 and port 3 are perfectly isolated. S32 equals S23 equals 0.
3. The final S-parameter matrix. Because the signal travels through a quarter wavelength line from port 1 to port 2, it experiences a 90 degrees phase shift, represented by -J. Power splits in half, so voltage drops by 1 over square root of 2. The ideal S-parameter matrix for a Wilkinson power divider is shown here. Row 1. Port 1 is perfectly matched, S11 equals 0, and power splits evenly to ports 2 and 3, 1 and 1. Rows 2 and 3. Ports 2 and 3 are perfectly matched, S22 equals S33 equals 0, and they are completely blind to each other, S23 equals S32 equals 0. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.